Welcome to this reaction video.
This is the 21st video in our series on abstract algebra.
Thank you so much,
Today we're gonna
Oleki,
look at
for suggesting this video.
homomorphisms and some of the classic
I will watch
isomorphic
every video
theorems
that
of
is being
rings.
sent.
So let's dive right
Nothing
into the
can stop me
definition.
from reacting.
So let's say we've got rings R1 and R2.
Okay.
And then we have a function phi from the ring R1 to the ring R2.
Okay.
So we call this function a ring homomorphism if it satisfies two conditions. So for all a and b in R1, we have phi of a plus b is equal to phi of a plus phi of b.
Okay.
And then phi of a times b is phi of a times phi of b.
Okay.
So in other words, this map respects both addition and multiplication.
Okay.
And then we've got some accessory definitions here as well. So if phi is bijective, it's called a ring isomorphism. Then we've got this notion of the kernel. So the kernel of phi is everything mapped to 0, the additive inverse.
Okay.
And then we have the notion of the image. So the image of phi, well, it's just everything that is landed upon by this function. Okay, so let's look at some examples, starting off with two examples that we won't even check are ring homomorphisms because it's fairly clear. So let's take the map from z
It's not going to be
Zn
fairly clear.
that takes an integer m.
I already know.
And it assigns it to its equivalence class inside of Zn. So
Okay.
if we're not working with z along with Zn, we often leave off the brackets of the equivalence class, but sometimes just to really make sure we know what we're talking about, we do that. And so based off of some things we proved earlier about how the equivalence classes work with addition and multiplication, this is a ring homomorphism. So maybe write out the details and you'll see the need for those results that we had previously. Then next we've got this really important ring homomorphism known as the evaluation homomorphism. And that goes from, well, really any polynomial ring to the ground ring. But for this example, let's take polynomials with entries in Q and send them to just Q, so the rational numbers. And what happens is that we take a polynomial p of x and send it to p evaluated at a. Like I said, that's the evaluation homomorphism. And in fact, the next video is going to be all about polynomial rings, so we'll see quite a bit with these types of homomorphisms next time. Then next, I'd like to look at a beefier example. Let's say that R is any commutative ring with characteristic P, where P is a prime.
Okay.
So let's recall the characteristic is the smallest number, so that if you add any element of the ring to itself, that number of times, you get 0.
Oh, okay.
Okay. Then the Frobenius map, which is the map from R to R defined by phi of R to R to the P, this is a homomorphism in this case. In general, it's not a homomorphism, which we'll see like maybe as an add-on example here. Okay, so let's check that this is a homomorphism. We need to check two things. We need to check the additive property and the multiplicative property. So let's do the additive property first. So let's do phi of a plus b. So let's notice that that is a plus b to the p power. But that might seem a little bit problematic, but it's in fact not. And that's because we can expand this out using the binomial expansion formula to a to the p plus
I do know this one.
p times a to the p minus 1 times b plus p choose 2 times a to the p minus 2 times b squared, all the way down to, let's see, we'll have p a b to the p minus 1, and then plus b to the p. Okay, so this might seem a little scary at the moment, but notice that everything in here is a multiple of p. We won't check that, but you can check that. That's kind of a well-known result. It's usually done in like a intro to proofs class, so that's generally a prerequisite for this type of class. But all of these are multiples of p. So I could maybe put this as p choose k is a multiple of p. In other words, it's congruent to 0
I am
mod
a thirsty
p
boy.
for all k from the set 1 to p minus 1. But that means that every term there that's overlined in magenta is equal to 0 because we're in a ring of characteristic p. So let's recall that by multiplication by p, we really mean repeated addition p times. So this object right here, let's maybe zoom in on that. What we really mean by that is a to the p minus 1 times b added to itself p times. But like I said, since we're in a ring of characteristic p, we know that's 0. Okay, so anyway, all of those things turn into 0, which means we're left with a to the p plus b to the p, which is phi of a plus phi of b. So the
Hopefully I
additive
did not miss
property
too much.
is satisfied. Now let's go on and talk about the multiplicative property, which is actually easier to check here. So let's notice that phi of AB will be AB all raised to the p power, but that's a to the p, b to the p, just by exponent rules. But that's exactly phi of A times phi of B. And let's notice that for this to be a ring homomorphism, we really needed the characteristic to be p. Let's note that we could look at a case where this doesn't work, maybe inside of the real numbers, for instance.
Okay.
And let's take p to be equal to 2, just as an example. And note that phi of a plus b here is a plus b squared, but multiplying that out, that's a squared plus 2ab plus b squared, which is in general not equal to a squared plus b squared, which is phi of a plus phi of b. And it's not equal to that because R does not have characteristic 2. Okay, so anyway, let's look at a couple more examples. For our next example, let's consider the ring of upper triangular matrices with integer entries. Okay. So in other words, they're of the form A, B, 0, C. And let's take the map phi from this ring to Z cross Z that takes this matrix to A comma C. And here the operation is just component-wise addition and multiplication. Okay, so let's make sure this works with addition. So let's introduce some notation just to make it look a little cleaner. Let's take matrix A to be A, B, 0, C. And let's take matrix B to be matrix X, Y, 0, Z. Okay, good. And let's notice that A plus B in this case is the matrix A plus X, B plus Y, 0, C plus Z. Just based on how matrix addition works. Okay, so now let's look at phi of A plus B. And notice that that will be exactly the ordered pair made of the diagonal entries of A plus B. So that'll be A plus X, comma, C plus Z. But now let's notice that this can be decomposed using the fact that Z cross Z has component-wise addition into A comma C plus X comma Z. But notice that A comma C is just phi evaluated at A and X comma Z is just phi evaluated at B. So here we have this is phi of A plus phi of B. But that's exactly what we needed for this additive property to be okay. Now let's look at the multiplicative property and make sure that's okay. We'll use our same matrices here, but let's notice that the product of these matrices can be calculated using the standard rule for matrix multiplication. So let's see, up here will be the entry AX. Here we'll have AY plus BZ, and here we'll have 0 and then CZ. Okay, but now let's notice that phi of AB will be equal to, well, all we have to do is take out the diagonal entries. So that'll be AX, CZ, based off what capital A, capital B is. Oh, but then here we've got component-wise multiplication. So this will be A comma C times X comma Z. But that's exactly phi of A and phi of B. So this is phi of A and then phi of B. Great. And now let's determine what the kernel is. So notice just the kernel by definition will be equal to all matrices, I'll call them capital A in R, such that phi of capital A equals 0, 0. That's taking the fact that our additive identity in Z cross Z is 0, 0. But it's pretty easy to write down which ones those are. Those are all matrices of the following form. We have 0, B, 0, 0, where B runs through all integers. Great, so that would be example of our kernel, or that would be our kernel in this case. All right, let's do one more example before we look at something else. Okay, so for our next example, we'll show that Z and 2Z are isomorphic as groups, but not rings. And I'd like to notice that this can be easily extended to the following statement. And this would be maybe a good warm-up exercise. And that is MZ versus NZ, where M and N are different. So MZ is not isomorphic to NZ as rings, but they are isomorphic as groups. Of course, they're isomorphic as groups because they're both cyclic groups, they're infinite cyclic groups. And from earlier in the course, we know that all infinite cyclic groups are isomorphic to integers. But let's prove that anyway. Okay, so let's define the following map. So let's define phi, and it goes from Z to 2Z by phi evaluated at an integer n equals 2n. And then I'll leave it to you to check that this is bijective. So that's fairly straightforward. In fact, we probably already did something like that in this course. Okay, and now let's show that this is a group homomorphism. So we'll have phi of m plus n is equal to 2 times m plus n. But now we know that multiplication distributes. We have 2m plus 2n. And indeed, that will turn into phi of m plus phi of n. Okay. So this shows us that we do have an isomorphism on the level of groups. So these are essentially the same group. So now we'll show that they are not isomorphic on the level of rings.
Okay.
So let's see how we might do that. So we're going to operate this by way of contradiction. So by way of contradiction, suppose that as rings, we have Z is isomorphic to 2Z, and let's say that is via the following map. I'll maybe call it psi because we've already used phi up here. So psi goes from Z to 2Z. And now let's notice that while we were showing that these were isomorphic as groups, everything with the addition worked out. So that means we probably shouldn't try to show something goes wrong with addition here. We probably need to show that it goes wrong with multiplication. Okay, so let's see how to do that. So let's maybe set psi of 1 equal to a, and then determine the possible values of a. So first off, let's notice that a squared is the same thing as psi of 1 times psi of 1. But then, since we're in a ring homomorphism, we can smash those together, and we'll get psi of 1 times 1, which is psi of 1, which is a. So that gives us the equation a squared equals a. But now let's notice that inside of the integers, which we really are inside of the integers, 2z is inside of the integers, that only has 2 solutions. That means a is equal to 0 or a is equal to 1. But we're in fact not inside of all integers, we're only inside of even integers. That's because our codomain over here is even integers. But since we're inside of only even integers, that tells us that this a equals 1 case is not possible. So that means we must have this case right here when a is equal to 0. But now let's notice that if we take any integer n, let's notice that psi of n is the same thing as psi of 1 added to itself n times.
Oh, that'd fuck it up.
Oh, but then since we're in a homomorphism, that's psi of 1 added to itself n times. But we've just determined that psi of 1 is 0 by the previous calculation. So 0 added to itself n times is 0. But since this n was arbitrary, that means we've just shown that psi is always equal to 0. But if psi is always equal to 0, then that means that this is in fact not an isomorphism. Because well, first of all, it's not 1-to-1, and then it also can't be onto. But that means that these two are not isomorphic as rings. We tried to get an isomorphism and ran into a contradiction. So we actually proved something a little bit stronger. We proved that the only ring homomorphism from Z to 2Z was the trivial ring homomorphism. So we'll look at more examples finding all homomorphisms between some rings later in this video. Okay, now let's prove a general result. So the first general theorem we'll prove goes like this. So let's suppose we've got a ring homomorphism, which we'll call phi, from R1 to R2.
Okay.
Then, given an ideal J of R2, so that's of the codomain, the pre-image of J, which naturally lives inside of R1, is an ideal. So let's prove that first. So let's suppose that J, which is in R2, is an ideal. And then we want to show that phi inverse J is an ideal, which means it needs to be a subring, and it also has to have the absorption property. Okay, so let's first show that it is a subring. Let's recall, in order to show that it's a subring, it needs to be closed under subtraction and multiplication. That's from the subring test, which we alluded to earlier and was probably on a homework exercise or something. Okay. So let's prove this subring test. So let's suppose that A and B are in phi inverse of J. Great. And then, like I said, we need to show that their difference is also in phi inverse of J. But in order to do that, we probably need to move into the ideal. So notice this means that phi of A and phi of B is inside of J. That's the definition of being in the pre-image. But now, since J is an ideal, it's a subring, but that means that phi of A minus phi of B is inside of J. But then since phi is a ring homomorphism, we can smush those together, leaving us with phi of A minus B. So let's see, phi of A minus B is inside of J, but that means that A minus B is inside of the pre-image of J. Okay, so that means that the pre-image is closed under subtraction. But we can also show that it's closed under multiplication. Notice that phi of A times phi of B is inside of J. That's because J is a subring and it's closed under multiplication. But since this is a ring homomorphism, this is phi of A times B. But since phi of A times B is inside of J, that's exactly the condition for A times B to be in the pre-image of J. So that means that our pre-image is closed under subtraction and multiplication. That makes it into a subring. And notice we didn't really use any of the major properties of J being an ideal here. We just used the subring properties of J being an ideal. So in fact, the pre-image of a subring is also a subring. Okay, so now let's prove the absorption property of an ideal. And so how do we do that? Well, let's suppose that A is an element of phi inverse J and R is an element of R1. So in order for this pre-image to be an ideal, we need R times A to be inside of the pre-image, and also A times R. Okay, but before we do that, we need to do a preparatory calculation, and that is, let's notice that phi of A is inside of J, and phi of R is inside of R2. But now, since J is an ideal, we know that it has the absorption property. So in other words, phi of R times phi of A is inside of J by the absorption property for J, and phi of A times phi of R is inside of J. Remember, we have to go from both directions here because we don't necessarily have commutativity of multiplication. But now we can smash these together both ways. This is phi of RA, and this is phi of AR. But then phi of RA being inside of J and phi of AR being inside of J tells us that RA and AR are in the pre-image of J. But that's exactly the absorption property we need for phi inverse J to finally be an ideal. So we showed it's a subring and we showed it has this absorption property, which means it is an ideal. Okay, so that's this first point proven. Now let's move on to the second point. Okay, so now let's do actually the next two bullet points at the same time. So let's suppose that I is an ideal of R1. And now first we'll show that phi of I is a subring of R2. But we'll do that only using the fact that I is a subring. And that'll prove this third point. And then we'll also at the end show that if it's in addition an ideal and phi is surjective, then the image is also an ideal. Okay, so let's get to this part first. Okay, so to be a subring, it needs to be closed under addition and or subtraction and multiplication. But recall, here we're looking at the image of I. Okay, so let's suppose that we have A and B inside of the image of I. So now A minus B and A times B also need to be in the image. Okay, but let's see, what does it mean to be in the image? It means that A is equal to phi of I and B is equal to phi of little j, where little I and little j are inside of I. Again, that's what it means to be inside of the image. Now let's notice that A minus B is equal to phi of I minus phi of j. But since we have a ring homomorphism, that's going to be phi of I minus j. But since that's phi operating on an element, that is inside of the image of I. Okay, so we took two elements from the image and their difference is also inside of the image. Now let's look at their product. So A times B is equal to phi of I times phi of j. Since we have a ring homomorphism, that's phi of I times j. But I times j is inside of I because it's a subring, so that's inside of phi of I. Okay. So these two properties prove that phi of I is a subring. And notice we didn't use surjectivity or the fact that I was an ideal. We only used the fact that phi was a ring homomorphism and that I was a subring. So that actually covers this third dot. So now moving on, let's show that we have the absorption property. And in this case, we'll need phi to also be surjective. So now, recall phi is surjective. And now let's get to it. So let's take an A inside of phi of I and some element little r inside of R2. Now we need to show that RA is inside of phi of I and AR is inside of phi of I. That would be the absorption property for the ideal. Okay, but now since we have surjectivity, that means that R is equal to phi of R naught for something which I'll call R naught inside of R1. Okay. And now we can essentially just get to it. So notice that A times R is the same thing as phi of little I times phi of R naught. Here I'm adopting our notation from right here. But now since we have a ring homomorphism here, this is phi of I R naught. But that's inside of phi of I because I is an ideal, so it has the absorption property. And then the same thing for A times R. This is phi of R naught times phi of I, again adopting this notation up here. But then since we've got a ring homomorphism, this is phi of R naught times I. But R naught times I is inside of the ideal I because Well, it's an ideal, so this is inside of the image of I. So that proves this second dot. Okay, so now let's move on to the fourth dot. Okay, so next we're going to prove the classic result about injectivity being related to the kernel. In fact, we'll prove that phi is injective if and only if the kernel of phi is 0. In other words, the additive identity. Okay, and sometimes we would say this as the kernel is trivial. Okay, so let's get to it. We'll do the forward direction first. So let's suppose that
I want to see this man's sleeves.
Injective.
They're going to be white as fuck.
And let's take A inside of the kernel of phi. And now what we'd like to show is that A must be equal to 0, meaning that the only thing that can be inside of the kernel is 0. But how could we do this? Well, let's note that since A is in the kernel, we have phi of A is equal to 0. But then since phi is a group homomorphism with respect to addition, this is the same thing as phi of 0.
Okay.
Oh, but then by injectivity, we know that A must be equal to 0. So that's really all we had to do. So since A is in the kernel implied that A was equal to 0, that tells us that 0 is the only thing that can be in the kernel. Of course, 0 is always in the kernel. Okay, now let's move on to the reverse direction.
I definitely knew that one.
So for this direction, let's suppose that the kernel of phi is the 0 set, so the set only containing 0. And then we'll show that this implies surjectivity. So that means we need an A and B in R1 such that phi of A equals phi of B. And what we'd like to show is that A must be equal to B. Okay, but if phi of A equals phi of B, that tells us that phi of A minus phi of B is equal to 0. But then since we have a ring homomorphism, that tells us that phi of A minus B equals 0. But that's exactly what it takes for A minus B to be in the kernel. So we have A minus B is inside of the kernel of phi, but the kernel of phi was a singleton. It was only 0. So since A minus B is in the kernel and the kernel is 0, that tells us that A minus B must indeed be equal to 0. But that immediately tells us that A is equal to B. So now starting here and ending here is exactly what we needed to show that this thing was injective, completing this reverse direction. Okay, so now we're going to look at the first isomorphism theorem for rings. Now for the first isomorphism theorem of rings. And we're going to go through all the details of the proof here just to be very clear. Although when we worked with groups, we also went through the proofs of the second and third isomorphism theorems. We won't do that here. We'll leave those as exercises. I think at this stage we can have those as exercises. They're really good practice to figure those out on your own. Okay, so anyway, let's suppose we've got a ring homomorphism phi from R to R2. So instead of calling that R1, I've just called it R. Then the map psi from R mod the kernel of phi to the image of phi defined by psi acting on the coset R plus kernel of phi is equal to phi of R is a ring isomorphism. So notice built into this is that the kernel is an ideal. The only thing we can quotient by is an ideal, but let's notice that it's pretty clear that the kernel is an ideal by the following quick remark. So the set only containing 0 in R2 is an ideal. That's always an ideal. Sometimes it's called the trivial ideal. But the kernel of phi is in fact just the pre-image of this set. But we just proved that the pre-image of any ideal is an ideal, meaning the kernel being the pre-image of an ideal is an ideal. That's all there is to it. And I'd like to notice that the diagram associated to this goes as follows. So we have R mapped to phi to the image of phi. Notice that if we restrict to the image of phi, this is onto. Then we've got this projection map, which I'll call pi, down to the quotient ring R mod kernel of phi.
Okay.
And then brought into the existence is this ring isomorphism psi from that quotient up to the image of phi. Okay, so like I said, we're going to go through all of the details. Let's show that psi is well defined first. So let's suppose we've got A plus the kernel of phi is equal to B plus the kernel of phi, and this is happening inside of R mod the kernel of phi. So we need to check that functions are well defined when elements of their domain have different versions. And that's definitely the case here. Anytime your elements are cosets, they could have different versions. That's here what we're supposing, that we've got two things that are equal, but maybe these are different versions of the same thing. Okay, but now by the coset equality theorem, we know this means that A minus B is an element of the kernel of phi. Again, that's by coset equality theorem. But now we can apply phi to this, and we'll get phi of A minus B is equal to 0. That's what it means to be in the kernel. Oh, but then since this is a ring homomorphism, we have phi of A minus phi of B equals 0, which means that phi of A equals phi of B.
Oh, okay.
Oh, but now extending this back off the other way, notice this really tells us that psi of A plus kernel of phi, which is equal to phi of A, which is equal to phi of B, is finally equal to psi of B plus kernel of phi. So the output of the function did not depend on which version of the same element we inputted, making this well-defined.
Okay.
Now let's prove it's a homomorphism. Now that we've shown this map is well-defined, we'll show that it's a homomorphism of rings, which means we need that additive property as well as that multiplicative property. So let's take phi of A plus kernel phi plus B plus kernel phi. Great. And let's recall that addition of cosets goes exactly the way you would want it to. Sorry, this should be psi over here. So that should be psi of A plus B plus kernel of phi. But now we can apply the rule for psi, and that'll give us phi of A plus B. But then since phi is a homomorphism, that is phi of A plus phi of B. But now that's exactly what we want it to be. That is psi of A plus kernel phi plus psi of B plus kernel phi.
Okay.
So the additive property is satisfied. Now let's look at the multiplicative property. So we have psi of A plus kernel phi times B plus kernel phi. So doing the multiplication on the inside using multiplication rule for cosets, that is psi of AB plus kernel phi.
Okay.
But now using our rule for psi up here,
I'm gaining
that's
so much
exactly
knowledge
phi
from this
of
man.
AB. But now we'll use the fact
got
that
Mike
phi
Penn.
is a ring homomorphism. That's phi of A times phi of B. But now we'll just take this equality in the other direction. So this is psi of A plus kernel phi times psi of B plus kernel phi. But that's exactly what we needed for this to be a homomorphism. Now let's show its injective. And instead of just finding the kernel, let's do it by the definition of injectivity, just for a difference.
I don't know what that is, to be honest.
So let's suppose that psi of A plus kernel of phi equals psi of B plus kernel of phi. And what we want is for these to be the same coset. But let's notice that by the definition of psi up here, that tells us that phi of A equals phi of B. Oh, but that means that phi of A minus phi of B is equal to 0. Oh, but then since we have a ring homomorphism here, that means that phi of A minus B equals 0. But that's exactly what it takes for A minus B to be in the kernel of phi. But if a minus b is in the kernel of phi by coset equality, that means that a plus the kernel of phi is equal to b plus the kernel of phi. So we started with psi evaluated at two seemingly different inputs was equal, meaning that the inputs were equal. Notice that this injectivity is kind of dual to showing that it's well defined. And that's because showing something is injective is essentially the same thing as showing the inverse is well defined, but that's neither here nor there. Okay, now let's show it's surjective. Okay, now showing it's surjective is going to be pretty quick. So let's suppose we've got an element that I'll call S inside of the image of phi. But what does it mean to be inside of the image? That means that there exists an R inside of R such that S equals phi of R. But now let's just take the coset R plus kernel phi and then we'll have it. So let's notice that psi evaluated at R plus kernel phi is equal to phi evaluated R, which is equal to S. So we found our pre-image. So it's surjective. So that finishes the proof of this theorem. Okay, so let's go back to our first example of a ring homomorphism and look at it in light of the first isomorphism for rings. So let's take the map that goes from the integers to the integers mod n, so Zn, that takes the integer m to its corresponding equivalence class. So I think this is clearly an onto map, so this is surjective. So that's pretty easy to see. Like everything here is just the equivalence classes 0 through n minus 1, and just those integers get mapped onto that. So that tells us that the image of phi is in fact everything. It's Zn. Now let's calculate the kernel. So the kernel of phi will be equal to all m inside of z such that phi of m is equal to the equivalence class of 0. But let's spell that out. That's everything inside of z such that m is congruent to 0 modulo n. Right? So that is because this phi of m is equal to the equivalence class of m. Remember, those two equivalence classes are the same exactly when this happens. Oh, but now let's extend this a little bit. So this is the same thing as n dividing m. But what does that mean? That means that m is equal to n times k for some integer z. For some integer k. Oh, but if m is of that form, that means that this set is just the set nz. In other words, the principal ideal generated by n. Okay, well, let's apply the first isomorphism theorem now. That tells us that z mod the kernel, which is nz, is isomorphic to zn, like that. And now let's look at a bigger application of this. So let's say that R is any ring with 1. So this is, like I said, any ring with a multiplicative identity. And then let's take phi from z to r defined as follows. Let's say phi of m is equal to the identity inside of r. I'll call that 1 sub r added to itself m times. And now what will the kernel be in this case? Well, it's pretty easy to check that the kernel of phi will be equal to nz, where n is equal to the characteristic of r. So if the characteristic of r is 0, then that's just 0. But if the characteristic of r is non-zero, then that's going to be like 2z, 3z, whatever the characteristic is. So anyway, what this tells us is two things. If the characteristic of r is equal to 0, then we have a copy of z inside of r. That also really explains this terminology of characteristic 0 based off of this like kernel here. And then furthermore, if the characteristic of r is equal to n, which is non-zero, that puts a copy of z mod nz inside of r. So
Okay.
the takeaway here is that there's a version of either the integers or the integers mod n inside of any ring that has an identity. So that really maybe compounds the idea that a lot of this is really motivated by the study of the integers. Okay, let's look at another example. So now let's look at the map that goes from polynomials with integer coefficients to integers, which takes a polynomial and evaluates it at 0. Now, let's notice that this is like very clearly surjective. We can check that real quick if we'd like to, but how does it go? Let's notice that n is inside of z adjoin x. It's just simply a polynomial with degree 0. There are no x's there. And then notice that phi of n will be equal to n, because if you set all of the x's equal to 0, which is essentially what this is doing, nothing happens. But that allows us to take any integer and map onto it. So all of this tells us that the image of phi is in fact just all integers. Okay, so that's good. Now let's find the kernel. So the kernel of phi, so that's going to be all p of x such that p of 0 is equal to 0. So in other words, when you evaluate this polynomial x equals 0, you simply get 0. But I think it's pretty easy to see what type of polynomial that is. And let's do this by calculation. So let's set our polynomial p of x equal to a0 plus a1x all the way up to am x to the m. And let's notice that phi of p of x, well, that's simply p evaluated at 0, that's a0. It's because all of the x terms cancel. But now if a0 equals 0, like we're saying if we're inside the kernel, then that means that p of x is equal to a1x added all the way up to am x to the m. In other words, every term has an x in it, but that means we can factor an x out of it. And if we do that, we have x times a1 plus a2x all the way up to am x to the m minus 1. So in other words, p of x is equal to x times some other polynomial. So let's write that down. So this is equal to x times q of x, where q of x is in fact allowed to be any polynomial. So that's by that side calculation. But let's notice that that is exactly the principal ideal generated by x, based off of our earlier study of principal ideals. And now applying the first isomorphism theorem for rings, that tells us that z adjoin x mod out by this principal ideal is indeed isomorphic to z. Great, so that's our nice result here. Okay, so now let's do some examples exploring what types of ring homomorphisms exist in certain situations. Now we're going to explore exactly how restrictive the notion of a ring homomorphism is by finding all such ring homomorphisms in a few situations. And of course, you could change the domain and the codomain kind of at will here and produce more exercises of this type.
Okay.
So for the first one, we're going to find all ring homomorphisms from rational numbers to rational numbers. And maybe the big takeaway here is the more structure you have, the more restrictive your homomorphism is. So the rational numbers are not just a ring, but they're a commutative ring with one. Oh, but everything has an inverse, or every non-zero element has an inverse. It's actually a field. So that means Q has a lot of structure, and all of that structure is kind of bad for producing different types of ring homomorphisms, as we will see. Okay, so let's get to it. So, well, we know it's a ring homomorphism, so it has to take the number 1 somewhere. So let's say it takes the number 1 to A. This is going to be pretty similar to a calculation that we did before, but you can't always do this. You can only do this sometimes. Well, we'll see how this doesn't always end with the same result. Okay, and now let's notice that in this case we have a squared is the same thing as phi of 1 times phi of 1, but that's phi of 1 times 1, but that's phi of 1, but phi of 1 is a. So just like before, that gives us the equation a squared equals a. But we know in the rational numbers, that only has two solutions. A is equal to 0 or A is equal to 1. Now, in some other places, that might have more solutions, as we'll see in our next example. Okay, but now notice if A is equal to 0, then we get the trivial homomorphism, and we can see that by the following calculation. Let's take a rational number x, so any rational number, and let's notice that phi of x is the same thing as phi of 1 times x, but that's the same thing as phi of 1 times phi of x, but phi of 1 is equal to 0 as we set a equal to phi of 1. So check it out. We started here at phi of x and we ended with 0. That means that, in fact, this is just the 0 function. But that tells us that perhaps more is going on in this case right here, this a equals 1 case. But let's just point out that this a equals 1 case is the case when phi of 1 equals 1. So it's important to keep that in mind. This letter a was just like a tool. The fact that phi of 1 is being sent to 1 is the important part here. So we're going to do this in a couple of stages. We'll first see what happens to integers, and then reciprocals of integers, and then we'll put it all together. Okay, so let's take a natural number m, and let's notice that phi of m is the same thing as phi of 1 added to itself m times. So let's point that out. This is m times. Okay, but then we know we've got a ring homomorphism, so we can split that up into phi of 1 added to itself m times. So there we have that is m times. But phi of 1 is equal to 1. If you add 1 to itself m times, you get m again. So notice we have, in the end, phi of m is equal to m for all natural numbers m. Okay, well, what about 0? Well, we know that the additive inverse has to go to itself. And we can check that just by looking at phi of 0, which is the same thing as phi of 0 plus 0, which is phi of 0 plus phi of 0, which is 2 times phi of 0, from which it follows very quickly that phi of 0 is 0. Now that's like a little more work than we really need to do, because we know as a group homomorphism, the identity has to go to the identity, and 0 is the identity of addition, and every ring is a group with respect to addition. But anyway, we did it. So now let's take negative integers, and we can essentially do the same thing. So notice that phi of m minus m, well, that's the same thing as phi of 0, which is 0. But then on the other hand, that's phi of m plus phi of minus m. Oh, but phi of m is equal to m. From this right here, we can move that over and solve the equation, and we immediately get phi of minus m is equal to minus m. Okay, so that's really good news. So we know that on the integers, all together after these three things, phi takes every integer to itself. Now, next, let's take a natural number n and see what happens to the reciprocal of a natural number. And we'll do this as follows. Let's notice that 1 is the same thing as phi of 1 from our previous calculation, but phi of 1 can be written as phi of 1 over n added to itself n times. So let's point that out. This is n times.
Okay.
And now, because phi is a ring homomorphism, we can split that addition up and we get phi of 1 over n added to itself n times. But that's exactly n times phi of 1 over n. Okay, so let's look at the extreme left. and right-hand side, and notice that that sets up a nice equation that we can solve. We have phi of 1 over n is equal to 1 over n. Okay, so far, what do we know? Well, we know that phi takes any integer to itself, and it takes the reciprocal of a natural number to itself.
Okay.
But that's essentially all we need to do. Let's take some arbitrary element of the rational numbers. Notice that an arbitrary element of the rational numbers can be written as m over n, where m is an integer and n is a natural number. And let's write this as phi of m times phi of 1 over n, using the fact that we have a ring homomorphism here. But now let's apply those results to write this as m over n, given that phi of n is m and phi of 1 over n is 1 over n. Great. Yeah. And, you know, that's what got ourselves restricted, or that's what all of these rules of a ring homomorphism applied to the rational numbers brought us down to. We have phi of m over n must be m over n. In other words, the only homomorphisms or ring homomorphisms from rationals to rationals are the trivial homomorphism and the identity homomorphism. Okay, let's do another example. So for our last example, let's find all ring homomorphisms from Z12 to Z28. Now, Z12 has an identity, I guess I should say a multiplicative identity, 1. And so we can play that same game that we did before. Let's set phi of 1 equal to a, that's something inside of Z28. And then we can perform this exact same calculation to get a squared equals a. And now I'd like to point out a little bit of a definition of a term here, and that is the notion of an idempotent. So an element is called an idempotent if it squares to itself. So let's notice that in the past we used the fact that the only idempotents in the integers or the rational numbers were 0 and 1. Those are the only things that square to themselves. But that's not true in an arbitrary ring. And in fact, it's not true inside of Z28. And recall that A is in Z28 because it's in the codomain of that function.
Yes,
so what should we do? Well, let's look for idempotents in Z28. And we can do that simply by squaring the elements of Z28 and seeing which ones return to themselves. I guess there's a little bit of a trick here, and other than 0 and 1, we only have to pick elements of Z28 that are not relatively prime to 28. So this is in the reverse of what we would usually do. But that being said, you could also just do it by exhaustion. So let's notice the following. So after either using that trick or doing it by exhaustion, squaring everything in Z28 and noticing this, we'll see that 0 squared is equal to 0. That means, well, that's sort of obvious. That's an idempotent Z28. We have 1 squared is equal to 1. That's clear as well. We have 8 squared. Well, that's equal to 64. But notice 64 is the same thing as 56 plus 8.
Yes.
But inside of Z28, 56 is 0.
Oh,
so that means, in fact, we have 8 squared is equal to 8 inside of Z28.
Of course.
Okay, so let's maybe box these idempotents. So we've got 3 so far, but in fact, there's one more.
There's one more.
And that is 21 squared. And it might seem like kind of hard to square 21 by hand and then reduce it mod 28, but there's a trick that we can do. 21 is the same thing as negative 7 in Z28, so we might as well look at negative 7 squared.
That is so
negative
true.
7 squared is 49. Oh, but let's notice that 49 is equal to 28 plus 21. But then 28 is 0 in Z28. So that gives us our last idempotent, 21. We have 21 squared is 21. So far, these boxed elements right here are the possible values of phi of 1. And those are the only possible values after checking all of the idempotents. But there's another thing to check as well. And that has to do with the order inside of the additive group. And this comes from when we did our original study of what type of additive group homomorphisms are there between, for example, Z12 and Z28. And notice what we'll need is that the additive order of phi of 1 must divide the additive order of 1. And I'm putting a plus there just to point out that I'm talking the order inside of the additive group. Okay. And then let's point out one more thing, and that is that this order right here is occurring inside of Z28. That's because that's occurring in the target space after we've mapped phi. Whereas this over here is occurring inside of Z12, inside of the domain. Okay, well, let's introduce our notation. So we have the additive order of phi of 1, that's the same thing as the additive order of A. That's what we set phi of 1 equal to. And then we know the order of 1 inside of Z12 is simply 12. So that gives us possibilities for this additive order of A. So it can be equal to 1, 2, 3, 4, 6, and finally 12, because it has to be a divisor of 12.
Okay.
So now let's also recall one more fact. And this is something that we proved when we were working with cyclic groups. So there's like a lot of little facts to remember. So this is one of them that shows up a lot of times.
Well, I'm going to remember it.
Is inside of Zn, the additive order of the number k is equal to n over the GCD of n with k. Okay, great. Like I said, we looked at this fact for the first time when we were working with cyclic groups, but it comes back useful every once in a while. Okay, great. So this will allow us to calculate the order of our possible values of A pretty quickly. So notice the additive order of 0 is equal to 1. Remember, the additive order is how many times you need to add something to get to the additive identity, which is 0. If you start with 0, you're okay.
Yeah.
So that means that this one works. This is okay because 1 is a divisor of 12. Okay, now let's look at the additive order of the next one, which would be the number 1. But inside of Z28, the additive order is 28. So we don't even really need to use this formula right here because it's easy to know the additive order of 1 inside of Z28. Okay, so this doesn't work. I'll just put a no up here. That is not a possible value of phi of 1. And now let's look at this. Let's look at the additive order of 8. That's our next possibility given that 8 is an idempotent. So that's going to be equal to 28 over the GCD of 8 with 28. But what's the GCD of 8 with 28? I believe it is 4. So that's 28 over 4, which is 7. But 7 is not a divisor of 12. It did not end up in this list. So this also doesn't work, which gives us one more possibility, and that is 21. The additive order of the last one, which is 21. So notice that's going to be 28.
28 over 7, which is 4.
The GCD of 21 and 28. But that's going to be 28 over 7. That's their GCD, but that will be 4. So that works as well. And notice, like, I got that right in the column with the other one that works. So those are our two values. We can take A to be 0 or 21. And now let's clean this up a little bit and provide a summary. Okay, so far we determined that the only places we could send 1 were 0 and 21 if we wanted to have a ring homomorphism. Okay, but what does that tell us? Well, if 1 is sent to 0, that means that phi of n equals 0 for all n inside of our domain, which is Z12.
Okay.
So that's our first possible ring homomorphism, the trivial ring homomorphism. Obviously, that's like the boring one. And in this one, if 1
So
goes
boring,
to
man.
21, that means phi of n goes to 21n inside of Z28. You know, we could also think about this as minus 7 and minus 7n if you want to write it that way.
Okay.
This is going to be true for all n inside of Z12 again. Great, so let's box that as well. And those are our two possibilities. So those are the only two possible ring homomorphisms from Z12 to Z28. Okay, so I'm going to give you a statement of the second and third isomorphism theorem for rings. If you're in my class, you'll be working on those proofs in class. Otherwise, I think they're good exercises to do. And then I'll also leave you with some warm-ups. Okay, so here is the second isomorphism theorem with rings. So let's let R be a ring with a subring S and an ideal I. Then S plus I, which is everything of the form little s plus little I, where little s comes from big S and little I comes from that ideal I.
Okay.
So that turns out to be a subring of R. And then S intersect I is an ideal of S. And finally, S plus I mod I is isomorphic to S mod S intersect I. And here's the idea of the proof. So you want to define the obvious ring homomorphism from S plus I to S mod S intersect I, and then apply the first isomorphism theorem. So that means you'll have to find the kernel. Well, you'll have to show it's onto and then find the kernel, and then you're essentially done. Okay, so now let's look at the third. Okay, now for the third isomorphism theorem of rings. So let's let R be a ring, and then we've got these nested ideals. I is inside of J, they're both inside of R. Then J mod I is an ideal of R mod I, and R mod I mod J mod I is R mod J. So you've got this like clearing the denominator action. And here's the idea of the proof. So you want to define the obvious ring homomorphism from R mod I to R mod J. You'll have to check that it's well defined and surjective. You have to check that it's well defined here because notice your domain is made up of cosets. And then again, apply the first isomorphism theorem.
Okay.
So find your kernel. Your kernel should be this J mod I. Okay, so now I'll leave you with some warm-up. Okay, here are three nice warm-ups based off what we did today. The first is an application of the first isomorphism theorem for rings.
I don't think I could do this, to be honest.
Let's show that Z cross Z mod MZ cross NZ is isomorphic to ZM cross ZN. The next, let's find all ring homomorphisms from Z10 to Z10. And then finally, let's recall that if D is square free, that means it's not divisible by any perfect square.
Okay.
Then Q adjoin the square root of D is equal to A plus B square root of D, where A and B are rational numbers. And then show that Q adjoin root 2 is not isomorphic to Q adjoin root 3 as rings.
Okay.
These are isomorphic as groups, and if you need to prove that, like as part of your exercise, you can, but they are not isomorphic as rings. So this is another one of those examples of a mathematical structure that's the same in one context, but different in another context. And that's a good place to stop. This is the 21st.
Fuck off. Thank you for watching this reaction video. It was quite interesting, but I could not follow it very well.